So this is our model of what we're trying to do for our project. We're trying to find the spring constant of the watermelon and how strong the force has to be for it to crush the watermelon. So our formula to find this is K equals negative F over X. F is the force in newtons, and then X is the displacement of compression. We're able to see that X is right here. It is the compression, um, the force, and we're going to assume that gravity is 9.80 meters per second squared. We have mass on top of the watermelon, and this is the force needed to break the watermelon. We're also assuming that the watermelon is flat, and this is how we were able to get the mass stuck on top of the watermelon to begin with.
We've given you a general overview of our model and what we'll be doing. I'll be explaining the math behind all of this. And we'll be looking at the equation K equals negative F divided by X, where K is a spring constant, negative F is force, and X is displacement in meters. This will give us information about K, which is the spring constant, which will give us information about how strong the watermelon shell is, which allows us to quantify how strong our watermelon is and how much force it can withstand. So we used force considering mass times acceleration equals force, mass in kilograms, and acceleration is gravity. We're assuming that's 9.80 meters per second squared, and we were able to find K. We plotted these out, plotting displacement X against force, and we were able to find a slope, which gives us information about how strong the watermelon shell is. Basically, we're ultimately able to see that we were able to add 5 plates, and barely adding a 6th one did the job.
Now we're heading into the experimentation portion, now actually placing the weights on the watermelon. We are making another assumption here that all of the weights are 45 pounds exactly. These are borrowed weights, and we're not quite sure. We could not find a scale nearby. Now, as we add these weights, you can see the watermelon on the bottom begins to deform, and we continue to pile the weights on. Eventually, we'll see once we get to the 4th plate, it actually became difficult to continue balancing the watermelon because look at the bottom of the watermelon. It is very deformed across the ground, and you can really see that we're trying to move quick here. Once we get this 5th plate, you can see the watermelon's under a lot of stress, and I'll let you see the 6th plate here. A very quick and sudden drop of the watermelon. We're going to play it in slow motion for everyone. Very, very quick and abrupt, and there was only a slight amount of pressure from that 6th weight, leading us to believe that it was the straw that broke the camel's back, if you will.
Now to do an overall assessment of the results that we experienced in this experiment. An average spring constant would be 21,645 newtons per meters, which is a reasonable value for a spring constant. When looking at actual springs and actual examples of spring constants, a normal value is around 30,000. So that indicates that our value is reasonable for obtaining a spring constant value for the watermelon. Now, obviously the watermelon is not comparable to a spring other than the fact that the spring is able to compress and come back to shape, whereas the watermelon, this shows the value to compress it, which shows the strength of the watermelon to break it. Our experiment went over about six weights added, where that 6th weight, just upon addition of it, broke the watermelon. And we can see after the first trial there, not a lot of movement, second, not a lot of movement, but then we gradually started to get more compression to where we got final compression, to where the watermelon broke. Ultimately, our calculations here seem reasonable, and our K value obtained gives us very good information about how strong the watermelon shell is.
That is the end of our video. Hope you enjoyed watching. Stay happy.